Hi, everyone. Welcome back. We're at the Stage Zero Knowledge Exchange Workshop here, co-hosted by PSF and the Department of Fisheries and Oceans. And I'm just going to get right to it. Our next speaker is Jared McKee with the U.S. Fish and Wildlife Service. I think we've got Jared all teed up here. So, Jared, I'll turn it over to you, and you can introduce yourself a bit more and get right into your talk.
Hi, thank you. Really enjoyed the previous talks by the other speakers. Thank you so much. My name is Jared McKee. I work for the U.S. Fish and Wildlife Service. I'm an engineer by training, and I'm also from Mississippi. So it was nice to hear Colin talk about Mississippi so much. Although in 1984, when Schum released his paper, I was all of 1 year old. So I got to experience all of this throughout my life. So, we're talking about low-tech approaches to project design and implementation. And to start off, I'd like to share with you an analogy about the invention of the airplane. So, the early history of flight control was plagued by a frustrating search for inherent stability, which was solved when the Wright brothers suggested that pilots be provided with sufficiently powerful controls with which to balance and steer. Similarly, many ecosystem restoration designers have sought inherent stability that early flight engineers attempted to create. However, this static design approach is arguably as inappropriate for managing complex ecosystems as it is for airplanes. By embracing feedback signals and dynamic controls in the design and management of ecosystems, as did the Wright brothers for airplanes, I will argue that restoration scientists and engineers will observe similar gains in ecosystem performance. Okay. So this is kind of what we'll be going through here, just a little outline of what we're looking at with the background, the scientific basis, some criteria, and then putting these criteria to work in your restoration designs and restoration projects. This can be found on the Stage Zero website that Janine mentioned, but yes, this is mainly based on a paper published in Bioscience in 2021. You can also find it on ResearchGate. So why do we write this paper, and why is this important? Well, working for the Fish and Wildlife Service, we were doing a lot of restoration, spending a lot of dollars, and emitting a lot of greenhouse gas to improve biological conditions, but we weren't really meeting these conditions. This is a wet meadow complex shown on the left there with an incised channel and generally degraded conditions, and on the right, you would be forgiven for thinking that this is a new development going in for row houses or even a parking lot or a Walmart. But this was actually a restoration project, surprisingly, with all the heavy machinery on the ground there. And you see what was built. This pond and plug project, as it's commonly called. The channel was filled in. Massive borrow pits were put in the channel, and a small effective discharge design channel at the Q1.5 was built in the northern part of this picture here. What happened was the channel blew out in the first flood. It returned to its incised condition, and much of that stream energy was moved onto these fine-grained sediments of a floodplain wet meadow soil, which did not like all that energy and all that flow being confined in one channel, despite the presence of channel-spanning rock weirs and other conventional structures in the kind of natural channel design vein. And it didn't just look bad. We had scientists with the Forest Service, mostly led by Karen Pope, looking at these restored and unrestored meadows and basically the lack of function that we were finding in restored meadows. So that was kind of our need identified and the problems that we were trying to address. And we thought that, perhaps we could work on this and could improve our practices by incorporating geomorphology, ecological engineering, and ecology to these systems. And thankfully, we didn't have to create this out of whole cloth. There's a great set of literature out there dating back, all the way to Schum and before. So Stanford and the Shifting Habitat Mosaic, riverine ecosystem synthesis, Margaret Palmer's work on river restoration, why it's working or why it's not working, and then her work and others presenting standards for ecologically successful river. And then paper that I really liked is Process-Based Principles of Restoring River Ecosystems by Beachy et al. Um, really laid forth the principles that you should be looking for in designing these projects. But Howard Odom was also talking about this with ecological engineering, and the amount of energy we put in should be small compared to that amount of energy that we're using in the system to restore and get these benefits. Of course, Michael Pollock and Joe Wheaton's work and many others talking about using beavers and implementing beaver analogs where beavers aren't present. And it wasn't, and this is backed up by long-term monitoring showing population level benefits to species by working with beavers and these beaver analogs. And of course, Clure and Thorne, their seminal paper that Janine used to actually divide the river restoration into different eras, pre and post, which is quite the compliment for these two guys. So we kind of think of three pillars surrounding social and cultural values of what we're building this on, but the pillars of ecological engineering, capitalizing off of the ecosystem energy, and the self-organizational capacity of rivers, as well as the riverine ecosystem theory and evolving riverscapes towards higher ecological values through restoring that connectivity, and the applied geomorphic analysis of Friars and Brierley and Condolph and Piguet, analyzing riverscape change and characterizing the natural processes there. This led us to kind of an ecological process-based river restoration framework. And this wasn't all. Like I said, starting back in '96, Bradshaw talking about helping a river to rehabilitate itself is really appealing. It costs nothing. You just have to set it up. You just have to allow the river to do the work and address the source problems. And they're likely to be self-sustaining. And they can be applied at a much larger scale when you're not recreating old forms. The ecological standards, abbreviated here from Palmer, but really important, is that guiding image of the dynamic state of river and increasing resilience and creating no lasting harm, kind of like a physician attending to a patient. First, do no harm to your river. And looking a little deeper into Beachy's process-based principles, they were really formative as well in our thoughts on this. Really, number one, targeting the root causes of habitat and ecosystem change. It's not just about recreating the form that you think the river should take. It's about removing those damages to the system, those anthropogenic constrictions and other activities that we've degraded our river systems and floodplains with, and then tailoring restoration actions to meet the potential and really matching the scale of restoration to the scale of the problem and being explicit in the outcomes. Of course, Clure and Thorne was a seminal paper on river restoration, redefining the stream evolution model. I really like the spiral / circular element, the evolution that's present in their alignment here. I think it really meshed with my understanding of rivers and ecosystems. And then Pollock et al. Looking at this as well, and how these beaver dam analogs and working with nature and the power of rivers can evolve these ecosystems into a higher state, something that we're looking for. So this led to the design criteria for process-based restoration of fluvial systems. Here we describe 4 design criteria to evaluate a project's potential: the expansion of fluvial process space and connectivity lost because of human alterations, the use of intrinsic natural energy to do the work of restoration, the use of native materials that do not overstabilize project elements, and the explicit incorporation of time and adaptive management into project design to place sites on recovery trajectories as opposed to attempts to restore sites via a single intervention. So we'll look at the space criteria, and it says project actions increase the spatial extent of fluvial processes and the connectivity lost because of human alterations. Stated as a question, when you're evaluating projects or looking at actions, do restoration actions reconnect lost fluvial process space, or do they just work within the current confined process space? That's one of your first clues as to what kind of restoration is going on here. So much of the degradation to fluvial ecosystems involves the confining and disconnecting of vertical, lateral, and longitudinal processes. This includes natural sediment movement, flooding, and fish and wildlife migrations. These arise from all kinds of conditions, including dikes, levees, roads, rail lines, and other human infrastructure. Grazing and mining and timber management also affect the vegetation and topography. This was touched on in the questions, so I hope this talk helps answer some of those questions. If not, ask them again. So some keys to success really is allowing that sufficient space, and I think we touched on it. I was excited to see space really called out in the questions and by the previous presenters. But why do we need this space? It really allows for that dispensation of stream energy. It allows for sediment deposition and erosion, and it increases that surface groundwater connections in accordance with the natural hydrogeomorphic and biological potential of the site. Reconnecting this fluvial process space increases the interaction of floodplain vegetation with the hydrogeomorphic processes. It adds further spatial and temporal complexity to the patterns of flooding, sediment transport, and erosion. That temporal complexity, I think, was kind of touched on one of the questions I saw on the list about floods of different orders of magnitude and how these systems work. It enables a river system to create and restructure the habitat, most importantly. And the space concept certainly isn't new or just in the Pacific Northwest. It's all over the world. In France, it's Espace de Liberté. In the Netherlands, I'm not going to try to pronounce that, but translated, it's room for the river. It's also known as the process domain, the functional process zone, the erodible corridor by Friars and Brierley in Australia, and the channel migration zone in Washington State. This top picture is a modeling effort on the channel migration zone, and the lower picture is really just showing how the river needs space and the potential alignments of the river over the years, and how it's really not locked in one place or in one configuration. This approach that we're working with the process-based approach really differs from the form-based approach, where in form-based, in-stream work is really extensive, heavily engineered, and it requires a huge carbon footprint as well as a disturbance footprint. That also burn a lot of carbon importing intrinsic material, whether that be rock or large wood, trying to create this stable channel form. And one of the goals is that the channel remains stable over time, which inevitably limits habitat forming processes. Whereas in the process-based approach, infrastructure removal is focused to create as large as possible habitat forming processes to occur. We need that space. By doing this and by focusing on just manipulating the infrastructure with heavy equipment, it requires a small carbon footprint and small disturbance footprint. That disturbance is generally located on areas that were previously disturbed. This helps a lot when working with tribes or when you're sensitive about cultural resource issues that may be present on your site. It also works with fluvial energy, sediment, and vegetation to develop the complex multi-channel system. The system remains dynamic, with habitat elements forming and disappearing and then reappearing elsewhere. That's that shifting habitat mosaic that we need, that rivers naturally exhibit, and how they've provided habitat over the eons. Now, here's a big table that I will not read to you, but I will give you a few seconds to look at. It can be found in the paper. Um, Even if you just take one line and just read it across and see the differences in kind of conventional objectives for habitat restoration versus how we would translate that into process-based objectives. And then the last two columns are really how that matters on the ground, how that changes the practices when dealing with restoration. So space and connectivity. It, Providing greater space for fluvial dynamics capitalizes on the ecosystem recovery and self-system recovery. We've developed a SOP for doing this. We'll run through it very quickly, but the document's available if anyone would like it. But in this method, practitioners indirectly restore habitat by removing those anthropogenic stream and system disconnectivities, and also allowing for natural flood disturbance and greater biodiversity. It requires a net gain in dynamic fluvial process space for flooding, channel mobility, and sediment conveyance. Because I'm an engineer, I frequently think in equations. So in these set of equations, process space is somewhat what we've talked about here, and then we also believe we've kind of developed this term, the stream evolution corridor, which is a little bit larger than the process space. And think of process space as that floodplain where the water's interacting with the surface and the sediment and the vegetation, whereas the stream evolution corridor kind of incorporates that hill slope as well, acknowledging that that's a source of sediment as well as large woody debris and other material for the river, and that the river is going to use depending on kind of the location and the flood flow events and whatnot. And really, the space criterion says that your PS sub F should be greater than your PS sub I, or your final process space really needs to be larger than your initial process space, what you started with. Here's a little look at Doty Ravine. Damien will get into this earlier, but you can see the SEC in yellow here. It's a little bit larger than the process space in green, and uh, and then you can also see in red the incised channel and the levees present, which was our initial process space starting with this, and how much we were able to restore and reconnect. Um, and you can see how these translate. Most of the time, your initial process space is much less than your SEC. That's what we've done historically in these rivers. We've changed a lot of these landscapes from depositional landscapes to threshold channels or even erosional channels, and taking them back to depositional channels and depositional reaches is really as simple as giving space back to the river. So, some source problems that you should look for on your sites. We've already mentioned a couple of them. I saw, people talking about dikes in the questions. But yes, used or abandoned roads, train tracks, levees, dikes, ditches, culverts, even redirected flow paths or straightened channels, and the unnatural stream armoring of riprap or even wood wrap, as we see in some cases, for the kinder, gentler locking in of streams. But source problems also include the impediments to natural biological forces, whether that's depredation of beaver, livestock grazing in the riparian, such that the only vegetation left is about lip high, and even the presence of non-native species in some cases, whether that be reed canary grass, signal crayfish, or other species that we run into that are damaging to our recovery. So this delineation of the fluvial process space is an assessment of the potential spatial scale of the project, and it encourages focusing on less on channel form and more on gaining space and connectivity at a valley scale. Really getting your head out of the channel and looking at what's around you, looking at your possibilities, and being able to delineate and identify the source problems that are limiting this connectivity. And for many projects, you may not be able to recover the entire process space, but you can some, and that's going to yield ecological benefits. Here's just a quick example. Once again, Damien may step into this more, but we can see in the top in 2017, a channel stream here we removed the levee on river left and started using vegetation and beaver dam analogs to create more roughness in the channel. At first, the channel just meandered a little bit to the side, a little bit to channel left here in the picture. But by 2017, after a couple of flood flow events, that channel had broken onto the floodplain and created that dynamic stage 0 river wetland corridor that we were really shooting for. And you can see how green, just as a measure of productivity, how green that landscape is. In the top picture, besides trees, the only green is the Himalayan blackberry out on the floodplain. In the bottom picture, on the floodplain, the only brown is the Himalayan blackberry, a non-native invasive species that we didn't really want out there, and now it's gone. It doesn't like its feet wet. It drowned out, and now native beneficial wetland vegetation has taken its place, as well as creating just a huge amount of habitat. So our next criterion was the energy criterion. It says project actions capitalize on natural energy within the system to do the work of restoration and to minimize the use of external mechanical energy. In this photo, you can see the top photo is the result of geomorphic work being done, those flood flows, depositing and eroding channels on the floodplain, depositing sediment on the floodplain. And then in the summer, after the flood flows, that vegetation coming in, really defining those channels, creating deeper pockets, habitat heterogeneity, shading, primary productivity in the channel. And this energy criterion is very similar to green architecture that uses the naturally available energy for as much of the work as possible. It could be solar panels and wind turbines for an energy efficient house, but here it's working with vegetation, it's riparian planting, it's working with beavers to really become energy efficient and just using your fossil fuels and your greenhouse gas budget just to do the minimum necessary in order to remove those anthropogenic constrictions, which limit the functioning and the ability of the vegetation and the biotic environment to form these stage zeros habitats. So the energy criterion really requires the consideration of the natural kinetic and potential energy, such as water and sediment, transport and storage, especially during floods, and along with solar energy used to drive vegetation growth, as well as the metabolic energy expended by animals, namely the beaver, but also others. And that beaver charismatic. That's why they were on the cover of this magazine. But working with energy really requires the designer to creatively maximize that system's naturally available energy to meet your goals. And you avoid the extrinsic energy use and heavy machinery equipment driven by fossil fuels and releasing greenhouse gases, which end up shooting ourselves in the foot. Climate change is an issue for all of our habitats, so let's not contribute to it any more than we have to, just to appease our ideas of form and idealized habitat construction. So a good restoration designer understands when, where, and how the natural fluvial and biological energy in an ecosystem is created, stored, delivered, and used. For example, how the system generates and moves sediment, wood, and other organic materials. Restoration design uses this knowledge to set realistic timeframes for project objectives. This doesn't occur overnight. You need process that in the word process has a connotation of it's going to take a little time. You need to work with it, and you should also set your broad specifications for acceptable types and configurations of channel forms. In that, immediately after you implement, it may not reach stage zero. As soon as you pull out, it's going to take a flood. It's going to take beaver moving into the system. It's going to take the chance for process to work. And it recognizes that working with natural energy sources requires the acceptance of stochastic outcomes. And this is a major departure from form-based restoration approaches, where you rapidly create an assumed reference or pre-disturbance condition through substantial input of fossil fuel energy. You're really working with the stream and nudging it in the right direction to help it create a sustainable channel form that provides the biological benefits that you're looking for. This fluvial energy can be used to reconnect laterally streams and floodplains, as well as longitudinally to reconnect upstream transport zones and downstream depositional zones. Addressing longitudinal connectivity is very important in these. The designer should look for blockages or modified flow paths outside the defined project area along the main stem or tributary stream paths to know what is possible and to know what's affecting the site you're working on. It's not all about where you're working, and it could also lead to projects in the future and strategic projects in the future, not just random acts of restoration. Sometimes an upstream culvert or road crossing needs to be upgraded, and this is integral to restoring that fluvial connectivity, ensuring the success of a downstream floodplain restoration project. This could also be dams or other source problems. So, process-based restoration also harnesses the biological energy, and this is the most fun to work with to me, especially in these alluvial stream reaches where vegetation shapes and directs the geomorphic and hydrologic process, as Janine and Colin really well pointed out in their paper about the stream evolution triangle. As degraded streams recover, ecological processes and hydrogeomorphic processes work together and vice versa, and they lead to these feedback loops between the two that lead to greater and greater habitat diversity and biological benefits. Some more ecosystem engineers, besides just the plants, include beavers, wolves. I'm sure everyone's seen the videos and the stories about the reintroduction of wolves to Yellowstone and how that led to this cascading effect wherein rivers were much improved, sediment loads were decreased, and eroding banks were much less prevalent. But a lot of these ecosystem engineers are no longer there, and that's part of a process-based restoration is thinking about what's not there and how you can support that or mimic it if possible. Although getting that there's no substitute for having actual beavers working in there. You can build all the BDAs you want, but a beaver is out there 24/7, 365, constantly working and moving and changing the environment in ways that we really can't do as people. The other examples, thinking about depositional reach, developing channel bars, and if they're colonized with fast-growing willows and other plants, these bars can stabilize and expand. And this creates the feedback loop for beavers such that they are harvesting the willow and moving and actually farming willows around your site and leading to increased habitat complexity, floodplain connectivity, and biodiversity. Biologic and hydrologic energy direct the biophysical recovery of the ecosystem and underscore the importance of expanding beyond the traditional hydraulic energy and geomorphic form considerations when planning. Like Colin was pointing out with Phillips and the biological energy in landscape evolution, that solar power and that biologic and metabolic energy expended just dwarfs the hydrologic energy. Other important sources include these large stochastic disturbances, including wildfires and landslides. And as Paul and others were talking about, these can be benefits. These can be boons to restoration. Although we often think about process-based restoration in terms of the moderate annual change, having your system set up and being prepared to capitalize on these major disturbance events create change a disaster into a restoration action. Uh, an example, with a large wildfire burning through a watershed, installing wood jams and low gradient stream reaches to capture erosional runoff can quickly fill incised channels instead of that sediment filling downstream reservoirs. The energy criterion discourages the use of external energy sources such as fossil fuels needed to drive heavy equipment to implement conventional channel or floodplain reconstruction projects. However, it is necessary to modify the infrastructure or to protect important infrastructure. By removing and reserving that heavy equipment primarily for infrastructure removal, the risk of developing the unstable habitat forms through channel design and construction is minimized. An existing recovery process may be spared from unnecessary soil compaction, the disruption of native seed banks, and the creation of favorable habitat to invasive species. Plus, as we said, greenhouse gases are limited. Every other, basically, yeah. Uh, uh, Sorry, I lost my train of thought there, but yes, but yeah, limiting our greenhouse gases, like every other industry is doing these days, is important. I think that's overlooked in the restoration community. But if housing developments and Amazon can look at their greenhouse gas emissions, then so can we, and it's probably more important for us to do it as well because we're actually fighting the effects of climate change by greenhouse gas emissions. And the disturbance footprint is limited. Working with tribes and really being um, conscious of that, as well as the dignity of rivers, which is a great talk that Colin gives. You know, limiting that disturbance footprint, I think, is quite important and quite appreciated by our project partners. When and it makes permitting much easier as well and much faster when you're just disturbing previously disturbed landscapes. So, for our materials criterion, projects use geomorphically appropriate materials to encourage channel evolution and avoid overstabilizing project elements. The design criterion for materials requires that they be locally sourced to direct fluvial and biological energy and reduce the reliance on extrinsic energy sources needed to bring outside emissions in. This also helps with our greenhouse gas. Native materials help ensure that largely immobile structures aren't built and that the natural recovery processes can work on these streams and develop stage zero conditions or the stage one conditions the streams are tending towards and we can help tend towards. The low-tech process-based restoration manual out of Utah State with Joe Wheaton and Wally McFarland and Scott Cheverdian et al. Is a fantastic resource. I recommend everyone check it out and use it. It has amazing detailed drawings as well as typical drawings. A lot of stuff that can be used in your restoration design pulled straight from the manual to be able to communicate with permitters and project partners what you're trying to achieve and how you're going to achieve it. And, these structures really prompt a recovery through small and strategic interventions. These structures help compensate for the past alterations that were aimed at consolidating flows and facilitating the water transport to accommodate agriculture, roads, bridges, and waterway commerce. These materials are strategically placed to accelerate the channel evolution from a single thread to a multi-threaded form. They help expand and accelerate aggradation. They encourage channel widening. They partition shear stress in the stream, and they create new surfaces for vegetation growth and succession. Structures made from locally sourced materials are used to accelerate as short-term tools the beneficial geomorphic processes and are not necessarily expected to persist through the winter floods. These structures are evaluated based on the process they induce and not their permanence. Structural failure is a benefit for the system. It can cause local erosion, but it doesn't inhibit natural processes. It can easily be repaired, improved, removed, made smaller, made larger in successive years. You're really working with the system to reach your goals. In contrast, installing permanent structures such as boulder-based grade controls or bank protection and otherwise fine textured channel floodplain systems can inhibit fluvial ecosystem development. We saw that in the first example in the California mountain meadow, where there were boulder-based grade controls throughout, designed just to spec as any professional designer would, but they were placed in the wrong area, and they were had basically had the wrong goals, creating a transport reach, a single thread transport reach through a depositional environment. So using these readily available, locally sourced materials, it reduces that upfront design planning and construction cost and allows for more rapid implementation over larger stream segments at a reduced cost, really doing more with less. These BDAs and PALs and hand-placed wood jams, they really exemplify these process-based structures. They're low cost, require minimal energy input, and have minimal construction footprints, and allow for that adaptive control over flow energy and sediment over time. And speaking of time, the time criteria, it says to achieve habitat objectives over time via restored biogeomorphic processes. And that sounds, pretty simple, but it really, I think, is a big idea that needs to be explicit in our restoration designs and restoration projects. It challenges that assumption that a project, once constructed, will function as intended without further need for management or adjustment, and explicitly recognizes that time is required for the interaction of physical and biological processes to create a naturally functioning ecosystem. Sorry, I keep looking down to do my little clicker here. It's not as responsive as I would like it to be, but I'm sure that's user error. So minimally intrusive but incremental restoration over time promotes the understanding of the system and helps identify actions most likely to restore the natural fluvial and biological processes that will not require ongoing maintenance. Project designers often assume projects will function as planned in the years after construction, but as we monitor these things and reassess, we see that this mostly isn't true. Things need some tweaking, and we don't get it right on the first go. And this time criterion really helps to avoid the expectation of that instant one and done restoration, which can really lead decision makers towards expensive projects with limited ecological benefit. Also forces the designer to anticipate how the project area will likely change over time in response to disturbances and ecosystem changes such as floods, droughts, beaver dams, climate change, and just the changing hydrographs that we're seeing all over, going from snowmelt dominated to rain dominated ecosystems in many of our mountains and higher elevations. Large floods can substantially affect sediment transport, deposition, erosional processes, but they don't happen every year. 20-year flood, only happens about every 10 years nowadays. So you need to work with that. You need to set your site up for success, and be prepared when the time comes and when the atmospheric river hits. Some performance evaluations say that it might require a decade or more to achieve project success, but measurable improvements in success many times happen much quicker, as documented in Wall et al. 2019, and as Damien will talk about in the Doty Ravine example, perhaps others. The time frame for process-based restoration projects to achieve success will be determined by how well and how effectively you can address the source problems, as well as the when flows come and when the biological species come, whether that be beavers or plant plants. And you can help that. You can release beavers. You can create BDAs to entice beavers in, and you can do riparian plantings or other plantings, wetland plantings, to really kickstart the process and shorten your curve there. So with time, it's equally important to measure whether a system is recovering as much as it is whether a system is recovered. Um, Really setting a stream on that restoration trajectory is hugely important, and starting that feedback loop where it's a compounding effect over time. And you can monitor this, and you should monitor this. Stream characteristics that Brian and Colin touched on their 2013 paper. Including total stream length, the number of confluence nodes and stream channels, the number of vegetated islands, and the extent of the permanently flooded or raised water table. These are all indications of whether or not you're on that recovery trajectory. And increasing these values over time really shows that. you know, Working within these larger time frames for system recovery, it improves your likelihood of occurrence of floods capable of doing this geomorphic work, and then followed by those periods of biological activity where vegetation is growing, beavers are moving in and working. And event-based monitoring is sometimes better to use, than sitting out there every month uh, trying to document incremental, 1 centimeter changes in deposition upstream of a BDA. I would say save your time and money and wait until a developed threshold trigger has been hit. Whether that's a 2-year flood event or beavers occupying the site, and monitor that directly after disturbance, and then following some post disturbance recovery, because it doesn't just happen during the event, but also in that time afterwards. So floods should generate a measurable improvement if you have addressed these source problems. If you haven't, if you're not seeing measurable improvements after a flood and after a lot of energy has been on the ground, whether that is fluvial energy or biological energy, then perhaps look more critically at some source problems, look upstream, see what's going on, and this really creates the opportunities for adaptive management. And once again, this really contrasts with conventional restoration approaches. Back when I was doing bank protection projects and single thread channel design and implementation, when a flood would come through, when rain started hitting the house hard, and you could just tell that there was going to be a big flow event, I almost couldn't sleep at night. I was so nervous, just praying that channel would still be there, that the what I had designed would still be there and hadn't blown out. Now, following a process-based approach, when the rain starts hitting the roof, I'm just smiling. I'm excited. I can't wait to get out there, because that work is being done and that you've set the stage for success for your project, in that you're going to see benefits, and you're going to see improvement when a flood event comes through. You're not worried about losing what you have because you did it right. So how do you implement these criteria? I'll try and do a brief run through of this, but most importantly is knowing your catchment, knowing your site. There's no substitute for being out on the ground, but the amount of data that we can do, and desktop reconnaissance, as I call it, is unmatched. We just get more and more every year. Forgive this list on the right for being heavily U.S. centric, but I'm sure all your good agencies in Canada are doing similar work, and you can find these sources and this data that can really help your understanding of the system you're working in. Some physical data that I think is critical is your topographic data, the geology and soils you're working in. Satellite and aerial photography that's come along in recent years is just amazing source of data. and then even infrastructure layers and road layers and other sources of GIS information that you can use in these projects, and also looking at species distributions, where they are in the landscape. If you don't have a beaver within 500 miles, then your BDAs are going to require a lot more work because you're the one maintaining them and not the beaver. But if you have beavers in the adjacent drainage or upstream or downstream, those 2 and 3 year old beavers will be moving out and will be expanding territory and looking for more places to settle. And they're smart. If they've got a halfway built dam already right there that somebody put in, some restoration practitioner, they might not like it 100%. They're going to work on it. They're going to fix it and make it the way they like it. But it's a good start, and they're more likely to stick in those areas. And then I wrote critical habitat here. That's more of a Endangered Species Act in the U.S. kind of terminology. But knowing where those rare species are and the species of concern, and making sure that you're not, you're applying that principle or the standard from Palmer. First do no harm. You don't want to if red-legged frogs are doing well in one area, you don't want to go in and totally change that just to achieve some channel form that you think is good, because it's providing habitat, and one of the few places providing habitat for some of these endangered species. So yeah, I mean, just looking at some aerial photography and the Google Earth time series is just awesome. I mean, just it's course data, but if you know what you're looking at, you can really get a lot from this stuff. I mean, this is Doty Ravine again. You can see 2004. There's no difference in the floodplain and the upland vegetation. It's all brown. It's all dry and desiccated. And this is a farm. This is a cattle ranch. They can't, they're not going to be. They don't have much food on the ground there anywhere at this point. You can see an irrigated pasture in the upper right hand corner, and see how much greener that is compared to even a floodplain. And that irrigated pasture is uplands. It's meters above the floodplain surface. It's dried and desiccated there. So yeah, I mean, looking at this time series, you can really glean a lot from what's going on the ground. Other things such, we have the national map in the U.S. The USGS does, really looking at the hydrologic connections, your tribs. All of this information is important to incorporate into your design and use to communicate with your partners and permitters. Soils maps. I wasn't really a soils guy until I started working with Damien, and he really turned me on to this. And they're great. They're a huge source of information. There's a lot of data out there, a lot of work that has been done, and they do a great job of mapping floodplain sediments. Mapping the process space more or less. It's a great tool that many times isn't used. Your topographic data. Where are you in your watershed long pro? Really important for your site. As Colin was talking about, these deposition zones, that's where you're going to get a lot of bang for your buck. Obviously you don't want to be trying to do this in sediment supply zones. That's not what that's not what that river wants to be in that location. It doesn't want to necessarily be this anastomatosing and a branching system. It is steeper, straighter. It's moving sediment out. It's supplying sediment for your downstream areas and for your transfer zones. Here's another project we worked on with the Mountain Maidu Tribal Consortium, Tasman Koyam, or the white man's name, Humbug Valley and Yellow Creek. You can see there's kind of a history of restoration here, and kind of below this road that's running across the valley, you can see another pond and plug project. We get a lot of these to come out and restore restoration. But in this project, there was that pond and plug project upstream, but there was no thought of addressing the source problem, which everyone agreed was this road right through the middle of the channel. Not only did this restoration project not address the source problem or necessarily improve the habitat, but it also damaged the infrastructure. This road washed out because of the redirected flow paths by the pond and plug project. And we try and improve roads, and they're a source problem, but they're also important for us. We need to keep them in as good a shape as possible as well, because we don't want this road base going into the stream. We don't want the fine sediment going into the stream, and we want to address the issues, including this incision and this concentration of flow through this one point in the valley, which really leads to higher velocities and puts a lot of energy on these fine textured floodplain soils, leading them to erosion and incision. But at this site, it wasn't all bad. In the lower right-hand corner, you can see the upper alluvial fan during this flood deposited a ton of sediment. This area was actually scheduled for pond and plug, but it was so expensive and they burned so much diesel earlier that they couldn't get to it. So thankfully, a few years pass, flood comes through, and that incised channel is no more. It's a dynamic stage 0 environment. More just getting to know your stream. The period of record on these things is, probably not as old as it is in England, but we've got at least back to the late 1800s. These are old General Land Office records from surveyors that first came through, looking at if this was first-rate land or second-rate land, if there was timber, if it was hay meadows and whatnot. But this showed a swamp. There it showed the Nasmonosing channels, anabranching channels, the multi-channel alluvial fan complex. It showed a lot of potential in this area, and just how it was in the past, and what it could be. Even in that top picture, in the top left-hand corner, you see wet marsh, and that's fairly confined compared to the rest of the valley, but it shows just how productive this area was before channelization and basically all the anthropogenic source problems introduced to this area. Topographic maps. There's a pretty long record of those as well, at least in the U.S. I mean, this one from 1886 is pretty good. Even in the 1950s, you can see some anabranching and some disconnectivity in the channel. And then, of course, they just keep getting better, and allow you to kind of see some of the source problems that have happened in the landscape. Getting to know your land ownership and land use is hugely important. Source problems such as ag pasture and timber production can really affect your restoration project. Not that they're always bad. It's just how it's done, like anything else. A glass of wine is okay at night, but a bottle of Jack is probably not going to live too long. So 1,000 head of cattle has a lot more impact than 250, or a clear cut has a lot more impact than a selective harvest. So looking at the geology, getting into your geologic maps, really shows your process space, shows your floodplain, your valley sediments, as well as what's contributing to that, where that's coming from, the volcanism, the fault lines, all important things to consider in your restoration project to get that holistic view of where you're working. And then aerial photos. If you have a private pilot like Dr. Brian Clure, they're pretty awesome too. Not only for planning, but also for communicating with your project partners. You can see here the main road on the right going through the valley, the pond and plug project upstream, and even how there's still remnants below the road where there still is that multi-threaded channel capacity and potential that hasn't been disrupted by pond and plug restoration project. I'll just click through these, but yeah, looking at your hillshades of these areas, you can really work to start thinking about your project and start delineating your source problems. You can really draw your evolution, your stream evolution corridor, your main channels, your historic channels. You can look at alluvial fans and other geomorphic controls. You can draw infrastructure in there that's impacting your system and those source problems. And at the end, you can have it really just jumped out to you what your source problems are. Where do you need to spend your time and spend your money or spend your diesel fuel to address these major disruptions to system process and system recovery. Um, of course, we, we don't have any good ideas yet on how to restore some of these restoration processes. We're working with some of these pond and flood projects, but it's similar to working with gravel mining alongside rivers where these giant borrow pits were created and plugged an incised channel and created a small little channel over on the side. But that's just kind of an interesting problem. And then you can develop, really useful communication tools for your partners, for your permitters as well, and be very clear in what you're doing and why you're doing it and how it affects the whole landscape. So you're really helping getting your head out of the channel and into the floodplain and into the system itself. Um, Working with energy, evaluating that catchment hydrology, realizing that the historic hydrology may not be the future hydrology, but at least estimating the frequency of events and what you can expect in the future, and how that will affect your the functioning of your project and the recovery of your project. Other sources of energy with solar and biofilms and periphyte and vegetation, beavers. This is all things to consider. Working with that stream energy and setting your time to restoration. Looking at what's on site, really doing a site inventory. What's there, how, and most importantly, how is it currently contributing to ecosystem recovery? Look for those little spots where beneficial things are happening, and think about how they can be used at other places on the site, or how you can bolster those processes. How you learn from the river and try and see what it's working on, and nudge it in the right direction if it's something that is beneficial to the biological goals, and think about what's missing and how you would replace that or even release those missing components. Um, you know, Doing your site inventory includes all these things. I think at one point there was a question about the bank and bank erosion. And, we do see that as a potential in some areas. If there's gravel or cobble in a bank and you can direct flow energy into that, then, you're going to uh, mobilize that sediment. And if you can create some, shear stress buffer downstream, then you're going to capture it in stream and start raising that stream bed. And overall, you just want to shift from that one-off restoration mindset into more of a stewardship mindset for these systems. Really get to know them, build a relationship with your site, work with your site, with animals and plants on the site. Be explicit in your goals and track those changes. We do this by looking at the hydrograph. You see 2008 to 2018, and really a channel moving from a 3S to stage 0 as we were hoping. I won't go through all these actions, so I want to save some time for questions. But we find this useful for communication as well as for our own just clarification of thought on actions and results, and what we would expect, based on hydrograph and other beaver occupation time for vegetation growth. So overall, space, give room back to the river. Materials, use what's there, what was there. Energy, engage the natural energy. Try and avoid reliance on fossil fuels for creating these forms. In time, you really want to evolve the ecosystem and not just create it. Here's an infographic that I worked on and was done by some very talented people in my office, and find it good to simply communicate, some of these takeaways and what we're working on and what we're hoping to achieve with this process-based restoration. And then that's it. Thank you. DFO Canada, I appreciate it. And Pacific Salmon, Oh Boy Productions, and Amy, thanks for working with me on my tech check. Colin Thorne for inviting me. Damien, who's been a great partner to work with in these restoration projects. My other co-authors, Janine, is an invaluable source of guidance and knowledge. Thank you to the participants for coming and being interested in this and giving your time for this morning and this afternoon. And then the Placer Land Trust and the Mountain Maydew Tribal Consortium. Without our landowning partners, we would not be able to do this. So